Today I'm going to start talking about binary search, and I've just in the last 20 minutes or so I've been just typing up the code. I was sitting in a meeting before this, and I thought I would get a head start on this because I also want to cover the assignment that was due last night. And so this is what I have. I haven't tested this yet. I just was, like I said, just coding it up. And this is the problem of implementing a binary search, which we talked about last time. And what this is where you have there's a prerequisite to do binary search, and that is the data that you're looking at. In this case, v, the vector v. It contains integers. This vector contains integers. That those integers must be in order. And they could either be ascending or descending. And I'll be assuming that they're in ascending order or non-decreasing. And so you can have ties in the vectors. So it should still work with ties. And so what this function does is when you call the function, you pass in a vector of sorted integers in ascending or non-decreasing sequence, and you pass in a value k, and you say find k in v. If you find it, return the index of k in v. If you don't find it, then return -1. And you'll see here in my code I'm returning -1 at that point. So what I'm trying to do here is if I as I sit inside the loop and I look at different values, I don't want to look at every value. I don't have to look at every value. I can search like it's a telephone book, and I can open it in the middle and decide whether k is to the left or to the right, and then just work with that half. Take that half and open that in the middle. Now I've got a quarter, now I've got an eighth, now I've got a 16th. And so you have the amount of data that you're dealing with at each iteration of the algorithm is halved. And that turns out that the number of steps you need to find something or to know that it's not there is log m. It's the base 2 logarithm of the number of elements that are in the vector. Because log base 2 of the size of the vector is the number of times that you can divide that vector in 2. And that's a lot. It turns out to be, as you can imagine, looking through a telephone book, that's a lot more efficient than doing a linear search, which is to look at one element after another. Of course, if the vector were not in sorted order, you would need to do a linear search. You don't have a choice. All right, so let's take a look at the test code. And here's some test code I just put together. And what I'll do is, just to make it more general, I will put in a tie here. And, well, let me wait on. I guess I'll put a tie in there. So 3, 6, 7, 8, 8, 12, 15, 36. If I search for -3, I should get -1 as the result. If we don't, -3 is not in there, so it should return an invalid index of -1. That's a sign that we didn't find it. But if we pass in 1 to the function, then we should also not find it. So I want to try a negative number and a positive number, both that precede the first value in the array. Just trying to stress the algorithm, stress my code, rather not. See if I can break the code with some good test cases. And here I'm passing in 0, which is the first element, so that should return an index of 0. And pass in a 5, that should not be found, so the function should return -1. I pass in a 6, that should find it, and the index is 1. I'll just put the indices here. This is index 0, index 1, index 2, and so on. I just want to make sure that test code is good. So 6 returns 1, 7 returns 2, 8 returns 3. Oh, we don't know which one 8 returns. So it would be the first occurrence. So we don't know actually. So it's some occurrence of 8. So maybe the algorithm returns 4. So I put a duplicate in there. So I'll need to modify the test code for that. So I'll say the algorithm, whoops, that's not going to work. I'll have to do it like this. That will not work. I'll need to save the index. I'll call it I. And then I should equal 3, or I equals 4. So there's my test. And that's a very general solution. Maybe this is maybe what I'll do there. Let me go backwards. I'm going to say, let's assume that this is strictly increasing. I'm going to change that because I want to make it simpler so we get the gist of the algorithm rather than dealing with the minutiae of the problem here. So we'll say V is strictly increasing. And so I'm going to take that test out. I'm just going to test that. I'm going to test that passing in 8 returns 3. So I just want to simplify that. So let's take 8 out here. So 6 is in slot 1, 7 is in slot 2, 8 is in slot 3, 9 is not there, 12 is in slot 4, 13 is not there, 15 is in 5, 16 is not there, 36 is in 6, and 46 is not there. So there's the test code. And we might want to try other vectors as well, but I'm going to start with this. And let's take a look at the algorithm here. Well, what we do is, you know, it's like bookends. We've got 2 bookends, one on the left. We start all the way to the left, all the way to the right. So S is the start index, which is 0. That's all the way to the left. E is the end index. It's all the way to the right. But actually, what I'm going to do here is go 1 past the last position. So E is 1 past the last element. And you see that a lot in different situations in computing. In the C++ standard library, you see that as a general pattern, that when an end index, when a start and an end is specified, the end is usually 1 past the last item. So that's when you're dealing with collections in the C++ standard library. Once again, the end, if you have a range, if you have a sequence, a start usually refers to the first element, the position of the first element, and the end is 1 past the last element. So I'm going to follow that. And I do believe in this case it makes the algorithm a little bit easier to code up. Although I'm not sure. There may be an equivalently simple way of coding it by assuming that, by setting E to the last index. I don't know. I would have to look at that in more detail. And here's, then we need another index, it's m. This is the middle, or the midpoint. So we're starting with 6 elements. And so if we take the midpoint, you know, it'll be here, 3. 3 is the exact midpoint. It's 3 before it, 3 after it. Oh, sorry, it's not 6 elements, it's 7 elements. If we had an even number, it'd be a tie for the midpoint. So M represents the midpoint. It's like the telephone book. M is the middle page. That's the page you're going to look at. I'm looking for Jones in the book. I'm not looking at the first page. I'm not going to look at the last page. I'm going to open it in the middle. We'll look for Jones right in the middle. And that's what we do right here. We start by comparing K. We're looking for K, remember. So I'm going to take my middle index M, look into V, so I have V sub M in that expression. Pull out the value that's at the midpoint in the range I'm looking at right now and compare it to K. If I found it, I'm done. I'm going to return M. I'm going to return the index where I found K in the vector. So here's the calculation for the midpoint. And so I take the difference between the end and the start. So the end would be big. Let's just do an example here. The start, in the first case, the start is 0. So it's 0 plus a 1 past the end, which would be 7, minus 0. And that's 7 divided by 2. What does that give us? What's 7 divided by 2? 3. It's 3. It's an integer division. If we get truncation, it's 3.5. It's 3.5, right? But we truncate. We drop the decimal part to get 3. That's integer division. So this here is, in fact, integer division. So that's how we break a tie. We go to the lower index. Once we compute the center, the middle, then once again we reach into V, pull the number out that's at that position M, and we compare it to the value we're looking for, K. That's what we're looking for. It gets passed into the vector. Passed into the function. If we found it, we're done. We return M. Otherwise, else. So if this condition is false, that condition is false, then we're going to go and evaluate the else clause. So we check another condition. All right, well, if M doesn't equal V of M, if K doesn't equal V of M, is K less than V of M? If K is less than the value at the middle, then I'm going to discard the right half of the range I'm looking at. So I'm going to set my new endpoint to the middle. Remember, this M is 1 past the last element in the range I'm looking at. So E is now 1 past the last item in the range I'm concerned with, because I looked at what's at M. I already looked at what's at M here. What's at M is not K. I don't have to look at what's at M anymore. So what I need to do is I need to look at the most, M minus 1. Anyway, so that's consistent with how we're thinking of E. E is 1 past the last element. All right, but let's suppose that K is not to the left of the middle. So the only case, if K is not at the middle, and it's not to the left of the middle, that means it's to the right of the middle. But, that's just, it has to be that way. That's the logic of it. if we want to check that, by the way, we can do this. We can put an assertion in there. That's what assertions are not actually, were not invented for test code. They were invented for validating your logic as you're thinking through the problem. And so, in fact, if we reach this point in the execution, that in fact k will have to be, in all cases, bigger than v of m. So we throw an assertion in there to say, yeah, crash if that's not the case, because if that's not the case, I got to rethink the problem. So you can just set that aside for a moment. So let's suppose we have, in fact, that k is greater than the value that's at that midpoint m, and then we're going to adjust the start position. Remember, the start position points to that item in the range that we're going to search. And we already looked at what's at m. So we're not going to point s at m. We're going to point s at 1 past m. So we just keep doing this loop, and see here, each time we iterate on this, E and S approach each other. And so they're going to keep getting smaller until E becomes equal to S, at which time this becomes 0. And E and S are the same thing. Let's see if that's right. This point is hard to explain, actually, because it's hard to understand it. So E and S are approaching each other. When these hit 0, let's suppose they hit 0, then M will be set to S. Let's reason through this. Let's suppose that E and S and M, they're all the same index. So here we're going to, well, if we find it, we're done. Well, let's suppose that the value is not in the vector. So I want to see if we're in fact exiting the loop and returning to -1. So this will be false, and then this will be false. I'm sorry, k is k, well, either k will be less than v of m or k will be greater than v of m. Let's take the two different cases. Let's suppose that k is less than v of m. Then E is set to m, and that's it. And we continue back here at the loop. So we don't change. So S and E still remain the same, don't they? So we're going to have an infinite loop there. All right, let's look at that. Let's try to fix that. There's an infinite loop. See that? I'm not doing anything. So should have found it by then. That's the problem. So E is getting to M, and we're not exiting. So what can we do there? How about if we did this? Is that going to work? Because here, this will be false. But are we going to exit the loop too early? That's the question I have now. Maybe we're going to exit the loop too early. If E reaches S, and then let's suppose in this calculation, let's suppose that here, E reaches S, then we're going to if E reaches S, that means E becomes S here, and yeah, can't think it out here. Well, let me take a break there. How can I explain it?
Why don't you use the midpoint as E plus S divided by 2 instead of S plus E?
E plus S divided by 2. That's even better, actually. That's good. It's the same thing, but it's, I'll do S plus E. That's the average. It's the same thing. Yeah, it is. It is. So the difference is what? So it's correct here.
Well, because
well, I think there's two cases. One is where the vector is even length, the other one where it's an odd length. And those are the two cases that we have to think about. And because either, all right, let's walk through an example. Let's suppose we have this example here. Let's say we have a vector which is 2, 4, and 6. So S starts at 0, and E starts at 3. And then the midpoint is what? 1. And also, let's suppose that we're searching for K equaling say 5. In other words, we're looking for something that's not in there. So here we compare 5, so we get M is 1. So 5 we compare to 4. It's not equal. Is 5 less than 4? No. That means we come into here, and S is set to M plus 1, which would be 2. And then S is less 2 is less than 3, so we continue the loop. So M is S plus C, that's 5 over 2. That's going to be 2. Now let's look at V of 2, which is 6. So that doesn't, we don't find it there. And here we're comparing 5 to 6. 5 is less than 6. So E becomes M. And then we continue the loop. Is S strictly less than E? It is not, so we exit. Is that sufficient? E is set to M. All right, let's take another case. Actually, we should code these test cases up. So it's the same K, and I'll do it like this. Let's take the same K, and we'll do 2 and 6. Keep it simple. So we start, S is 0, E is 2. So we, when we enter the loop, we have S is 0, E is 2, so M becomes 1. And so we don't find it, so this is false. And then we compare 5 with V of 1, which is 6, so that is true, so E becomes M. So E becomes 2. E becomes 1. We compare S with E, and S is still smaller than E, so we continue. And this time we compare, we calculate M. M is 0 plus 1 over 2. That's 0. Now we're looking at slot 0. That has a 2 in it. K is bigger than 2. So we come down to here. Now S becomes M plus 1. So S becomes 1. So S has reached E. And so we reject here. All right, we got to do. It takes time to do this. Here's the next test I want to do. Let's see if we can find it. Let's say K is 2. S starts at 0. E starts at 2. Oh yes, at 3. Thank you. Good. Thank you very much. That's great. And M is we're going to enter the loop with S as 0 and E at 3. So M becomes 1. It's 3 divided by 2 is 1. Do we find it? So V of 1 is 4. So 2 is less than 4. So this is the condition that's true. So we assign M to E. So E becomes 1. And then we check the loop condition. Is S less than E? It is. All right, let's recompute M. S plus E is 1 divided by 2. That gives us 0. Now we're looking at V of 0, which is 2. We find it, so we return M, which is 0. So that's correct. Let's try another one. Let's do even numbers. I mean, even number of elements. So let's start with this vector, 2 and 4. I'm searching for 2. Does the algorithm find the 2? Does the code find the 2? So S is 0, E is 2, that's the length of the vector, it's one past the last element. And let's look at M. M is S plus E over 2. That's going to give us 1. So we just entered the loop. We set M to 1. So we're looking at V of 1, which is 4. So K is less than that. So this is the condition that's true. And we set E to M. So E becomes 1. And then we check the loop condition. Is S less than 1? It is. Let's recompute M. M is 0 plus 1 over 2. That's 0. Now M is 0. So we're looking at V of 0 here. So V of 0 is 2. We compare it to 2. We found it. We return M. That's correct. So it's not a mathematical demonstration, but it's going through a lot of test cases. And let's go ahead and code those up, actually. We should code all of these just to check that we got it right. So we're testing, what I'm doing here, I'm testing 4 cases. And 2 of the cases have an even number vector, and 2 of the cases have an odd number vector. In each of those subcases, we test the code to see that we don't find something, and in the other case that we do find something that's there. Let's go ahead and do that. So I have a vector of in. I'll call it, you know what? I'm just going to use V. So that's safer. I'm going to call clear. I think I can call clear. Let me test that. I think clear is a function. Don't need that. All right, it runs, so clear is a function. All right, let's push back 2, 4, and 6. Two, 4, and 6. And then when we call binary search, just do it up here. We call binary search with k equaling 5. Should return a -1. It doesn't find it. So that's this test case that we looked at. All right, let's clear it again. And this time we're going to push, I'm going to do them out of order here. I'm going to keep the vector at 2, 4, and 6. This time we're going to search for 2. It should find it, which is, it's in position 0, so it should return 0. And now we're going to clear the vector again. This time we'll just push 2 and 4. Actually, this is the same vector, isn't it? We didn't have to clear. That's the same vector. Let's search for it like that. So when we look for 2, this returns 0. Sorry, we look for, what was the We were looking for a 5, right? Oh no, we passed in a 6. And we started by looking for a 5. And that returned a -1. And then we pass in a 2. And that should return 0. You know, it's easy just to add a few more test cases to make this complete. And so we have an even length vector, an odd length vector rather, and an even length vector. This is what I would consider a complete set of test cases. If we first search for a value that's too small and we don't find it, then we search for a value which is in the first slot and we find it. And then we search for a value that's between the first 2 slots and we don't find it. So we're really doing a comprehensive test here. Let's pass in 4. 4 will find it in position 1. And 5, we will not find 5. But 6 will find 6 in position 2. And the final test on that vector will be to go past the end, as they will look for 7. There we go. That's a complete set of tests right there. And let's do the same thing for here. So we search for 1, we don't find it. When we search for 2, we find it. And then if we search for 3, maybe I'm going to make it simpler there. This could be 4, just to keep the pattern the same. So we search for 1, we don't find it. We search for 2, it's in slot 1. We search for 3, we don't find it. We search for 4, it's in slot 1. And then we search for 5, we don't find it. And that's it. That's pretty comprehensive. Oops. Let's try it. Great. I got it. I want to say the weakness of my presentation is I didn't really prove it mathematically. And you know, I was a little lazy about it. I would need to prepare that. I would have to present a mathematically rigorous proof for this. But I did demonstrate how to make a convincing case with test data, hopefully. All right, one way to prove it would be to use what's called induction, but I'm not going to get into that, and I'm just going to move on because I've got other things to do. All right, any questions about this, by the way? So you're responsible for this algorithm. So you need to be able to produce this on the final and on the quiz 3. You're not going to need to write all that test code. So I'm not going to ask you for a comprehensive test like that. But you need to know how to write this out. Okay. Now I'm just assuming you want to look at the assignment. Is that the case? Okay.
Is our assignment for this Saturday?
What date did I give?
Yeah, I turned it down to 24.
So I think that's right then. Yeah. We don't have it. It's the end of the quarter, right? So we can't delay stuff anymore. We gotta get it done now. I think we've got enough time to get assignment 4 done. Yeah, I'm going to show you assignment 3. That was due last night, right? Yeah. So I'm not going to show you assignment 4. You got to do assignment 4 on your own. All right, let's. On Saturday night. Yeah, 12 o'clock. So you can, after 12, you go out and party. That's the idea. Huh? I submit it in the way you normally do. Huh? Oh, you can't like secure shell or anything like that? Then email it to Jaren by 12 o'clock. You can CC me as well. Okay. All right, let's, what is it? Assignment 3, which is here. Actually, this is A3, say 1. Actually, what we'll do here is we'll just figure this out without running the code. I'll get the. You don't really need to run this code. Let me try this. All right. Write a predicate function that called same length that checks whether 2 vectors have the same number of elements. And it returns true if the 2 vectors have the same size and false otherwise. Oh, that's hard to read. Let me put that right there. A declaration is in figure 1. The function takes 2 vectors as arguments and returns true if the 2 vectors have the same size and false otherwise. Oh, the same length. Oh. Just that they have the same length. So that's a pretty easy one there. That's you just return a dot size equals b dot size. Just a one-liner. That's it right there. That's the answer for that one. Any questions? Okay. That's a trivial one. All right, so write a predicate function that checks whether 2 vectors are identical. In other words, they contain exactly the same elements in the same order. A declaration is shown in figure 2. The function returns true if the 2 vectors are identical, otherwise it returns false. All right, for this one, we need to first check that, make sure they have the same size. So if a dot size is not equal to b dot size, then let's return false. They're not equal. So that's one requirement. Now let's check the next requirement. They're the same size. So let's examine each element of each vector. The corresponding elements at the same indices should be the same. So it's well, we're going to take a variable I, we're going to range across all of the indices of A and B. So if we find one, if we find that A of I, so for each I that we look at, if we find one where A of I equals B of I, we find an index where we have, I'm sorry, that's not equal, that should be not equal to. If we find an I where the two values are not the same at that index, then we know that the two vectors are not identical. But if we pass through that loop and we don't find any pair of values that are not the same, then we know that they're identical. Any questions on that one? This is identical. I want to make sure that the sizes are the same. Otherwise, you know, if B were to have one extra element on it, and we base our loop on the size of A, we wouldn't notice that B was different than A. If A and B were equal on all their elements except B had one additional element, see, this code would be insufficient to find that. So we want to check first that the sizes are the same. Okay, how about is non-decreasing? Write a predicate function called is non-decreasing that checks whether a vector of integers contains values that are in non-decreasing order. And so we have some, here's the example. It will return true for this vector. That's non-decreasing. In other words, it's increasing with some ties. But if the elements were out of order, in this case 2 follows 6, that would return false. All right, let's implement that one. So we need to look at what I'm going to do is look at pairs of values, and I'll just range through the vector and check that every neighboring pair of values are in the right order. So for integer I is 0, I less than b dot size, plus I. If A of I if A of I is bigger than A of I plus 1, I said that's a square bracket, then we found a problem. Otherwise we'll return true. Now, there's a problem here, of course. I just went through this fast. I've got to check the edge cases here. When I hits v dot size minus 1, right? when I hits v dot size minus 1, then I is still less than v dot size, okay? So let's suppose we're at the very end. The last I that we get, is one less than the size of the vector. It means the last I we get in the loop is a valid index, the index of the last element. But if I points to the last element, then I plus 1 is invalid. So we're going too far. You can see here we're going too far. So we can't stop. We got to stop one early here. And that's important for the problem. Can I repeat that?
Yeah, please.
About the going past the end?
Yeah.
Okay. Here, see, what we're doing is we're letting I take on different values, different possible indices, because we want to compare A of I with A of I plus 1. So we want to look at, for each, you can imagine these tiles here on the floor, okay? And I position I on this tile. And I want to make sure that I'm not bigger than the one in front of me. If I'm bigger than the one in front of me, I'm decreasing. There's some decreasing in there. So for each tile that I step on, I want to look one forward. But if I don't want to step on the last tile because there's nothing past the last tile. So we don't want I to go to the very end index. We want it to stop at one before the last index. This might help you think about it as well. This is at it. If we do I less than or equal to, this would have to be 2. If we're going to let I go all the way up to v dot size, because remember v dot size is already 1 past the ends. So v dot size minus 1 would be the last index, and v dot size minus 2 is the index just before the last index. So if that's easier for you to think about, you can do it like that. But you don't generally see that. It's not the style that's predominant. The predominant style would do it like this. So I'm showing you the common way to express this solution. All right, let's look at this one. Suppose that that array of int A has rows, and columns, or rows and columns are some constants. So they would be declared like this in code. But we don't. The idea there is we don't know what they are. I don't want you to use 3 and 2. Just this is an example. So rows are set to something, columns are set to something. Implement a function called add3 that uses a loop nested inside another loop to add the value 3 to each element of the array. A declaration of the function is shown above. I'll just leave that in there. So we want a nested loop. So we have a two-dimensional array. It's got rows and columns. Let's let I range across the rows. And let's let J range across the columns. So it's a nested loop. And then we just take, you know, what's at I and j, and add 3. That's it. So that hits every cell in the array. That's the point there. And the thing that I want you to sort of grapple with and understand is how to work with a two-dimensional array. And normally you would get something like a nested loop like this to process, to look at all the elements in that two-dimensional array. So you look at each individual row, so you get a loop that's running an index down through the rows, and then you've got a loop inside that. For each row you look at, you need another index, say j here, to range across the elements in that row. And then for each of those ij pairs, you can access that cell at that location. All right. Let's look at this one, random fill. Implement the function random fill declared in figure 5 so that it fills the vector v passed into it with 100 distinct random numbers. That's the hard part, is how to make them distinct. Distinct means that a given number can appear at most once in V. Use rand. Assume that V is empty when it's called. So V is empty. We'll want to put 100 random numbers in it that are distinct. We're going to use rand. So we'll need a loop here. I'm going to use a while loop because I don't know how many times I'm going to do this. So while something. I'm going to make it an infinite loop to begin with. And I'm going to go ahead and generate a random number n. And then it'll be like this, you know, if n is not in V, then append it to V. That's what I'm going to do. And if n is already in V, I'm just going to continue the loop and try a different n. And n, you know, rand returns lots of different integers, so I'll certainly be able to find 100 different ones. So how do we check to see if n is not in V? Well, I'm going to start by defining a Boolean variable called found. And I'm going to say that, I'm going to start by saying we didn't find it yet. Found is false. We didn't find n in V. But let's go ahead and I'm going to look at every element in V and compare it to n. If I found it, if I find it, I'm going to set the found variable to true. So if V of I is the n, then found is true. We found it. Otherwise, we finish the loop and found remains set to false. You have to do it this way. You can't do it the other way. You can't start by saying found is true and then set found to false. You can't work it that way. It doesn't work that way if you think about it. So you can't get it to work that way. Because found is true means we only found one case. We found one thing. Well, found equals false means we looked at every single one and we didn't find it. So you have to start with found equaling false. And that's the point where students usually get confused about. They like to start setting found in many cases the true there, and it's never going to work. And so after we finish that loop, actually, if found is true, we don't even need a found variable now that I think about it, but I'm going to keep it there anyway. So if not found, if we didn't find it, that means it's a good number. And we'll take v dot pushback and we'll put it in there. But here's the thing. You don't want to loop forever. So we want to change the loop condition. We're going to loop while v dot size. As soon as it's 100, we're done. So v dot size starts at 0. But now that as I'm working this out, I realize that it doesn't need to be this complicated. So I'm going to show you an alternative solution. We don't need a found variable. If we find it here, I'm just going to continue. So here I'm using this keyword continue. So if I find, as I scan through V, if I find n in V, then n's a bad number, I got to generate a new one. So I don't want to push back n. I just want to go back to the top of the loop. So I check this condition. That's got to be true because I didn't push back anything. It was true before, it's going to be true now. And then I generate the new random number here. Which one's easier for you to understand?
I have a question. Would continue skip the inner loop, or would you have problems because you have a nested loop?
Continue inside a nested loop. Continue will go to the inner loop. You will not be able to jump to the outer loop.
So wouldn't you just run the same line again in that case? Because you have
No. There's. Oh, I see what you mean. Oh, you're right. That doesn't work. God. This is dumb. Yeah, this is totally wrong. And so this will not work. Thank you very much for pointing that out. So, yeah, I wasn't even thinking.
I used while true and gray.
Huh?
Or I thought I used after that part. I used while true and gray.
You can do break here.
Well, wait. I used something like while true and gray.
But here, this isn't going to work either. So yeah, no, this is not a good solution. Thank you very much for putting that out. I don't know. I'm thinking about something else at the same time I'm doing this. I'm going to do this every quarter. This won't work. That's right. So continue doesn't work. But break here isn't going to do it either, right? Because we're going to hit here.
I did something with it. I think what I did is I just had a...
Did you use a Boolean value?
I put int n equals random inside the while in the same loop.
Yeah.
I made the loop instead of a for loop, it was just while true.
Yeah.
And then I put immense break as this. And I instead of the conditional was if I did another loop inside of it to try to find no, so if you add another loop that says
You mean a third loop?
So yeah. From int n equals rand, and then stop before push. While run that and put that inside while true. And then
I would say, I wouldn't want it. We have a solution that works with 2 loops.
Yeah.
I wouldn't want to go with a third loop. Yeah, we're running out of time here, so I can discuss that with you in lab.
I can't even remember what I was.
Yeah, so this is bad. This one is, please remember, this one is no good. Take that one out. That does not work. Must have found in there. That's it. That's all for the assignment. Any other questions, Okay.